Since we have some new guests today, I briefly introduce the platform Digitize Wood. Our platform fosters knowledge transfer between the research at the Cluster of Excellence IntCDC at the University of Stuttgart and practice in timber construction in Baden-Württemberg and beyond. And in our regular network meetings, we discuss different current topics with speakers from the cluster as well as the industry. Since the Cluster of Excellence is international and we have guests even from New York today, but also from Germany, we will have lectures in English and German. And yeah, because we want to make the network accessible to international participants and local participants as well. And during the discussion, please feel free to speak in the language you prefer, and we will help you out with translation if required. So, and now Moritz will give you an overview of the last network meeting and introduce you to the speakers.
Yes, okay. Thank you, Julia. Oder ich komme zum Deutsch rüber. Ich mache eine kleine Vorschau von unseren Vortragenden. Einmal Katrin Jonas, wurde ja schon gerade erwähnt. Da geht es um Designing with Families of Parts von Gropius. Und als zweiten Vortrag, wenn er nachher hoffentlich hier mit einsteigt, dann den robotischen Holzbau von Hans-Jakob Wagner. Und wie wir es auch die bisherigen Veranstaltungen gemacht haben, einen kleinen Rückblick zu den vorangegangenen Events. Und dazu einfach mal hier die 3 Vorträge, um die es letztes Mal ging. Also wir hatten das letzte Mal einen aus der Industrie, das heißt Aktivhausbau, wo es ums modulare Bauen ging. Dann 2 Vorträge aus dem Bereich der Forschung. Das war einmal vom IFAG, wo es um historische Bauten oder um die Vergangenheit ging. Und dann vom ICD, das mehrgeschossige Holzbauen. Als zweites ging es um das historische modulare Bauen in den 60er, 70er Jahren des letzten Jahrhunderts. Und da hatten wir die Alia Rappaport bei uns. Und es ging zum einen um vielleicht die Fehlschläge, die es damals gegeben hat. Wir haben verschiedene Beispiele gesehen. Hier zum Beispiel, wie man es auf der Seite sehen kann, adaptive Architektur über Frei Otto oder modulares Bauen im Sinne von einer Metastadt. Das war sozusagen dann der zweite Vortrag. Zwischen eingeschoben habe ich hier auch noch ganz kurz den Forschungsbereich. Wir haben ja viele Forschungsprojekte hier und genau wie dieser erste Vortrag aus der Forschung beim letzten Mal und dann der zweite, ging es hier in dem Fall eben um ein Projekt, was eine spezielle nicht technische Perspektive sozusagen zugrunde legt. Das heißt, da geht es um Architektur in einem historischen und auch soziologischen Kontext. Und in diesem Kontext werden einfach neue Bauweisen, also alte Bauweisen untersucht, die Fehler analysiert und auf der Basis dann geschaut, wie neue Typologien entwickelt werden können. Und das war dann auch entsprechend der zweite Vortrag von Hanna Svatos-Radnevich. Ich glaube, Hanna ist heute auch da. Ich hoffe, ich habe es wieder richtig ausgesprochen. In dem Fall, genau, wurden eigentlich viele Bauwerke analysiert. Und es war dann zum einen der Fokus auf das, was aktuell in Holz möglich ist, aber eben auch, wo die Grenzen vom jetzigen Holzbau sind in Bezug auf modulare Bauweise, was wir im ersten Vortrag da gesehen hatten. Und das ist sozusagen auch der Anknüpfungspunkt dann an den Vortrag von heute, wo ja praktisch der Multistory, also der mehrgeschossige Holzbau, ein relativ großer Forschungsschwerpunkt ist und hier eben aus der Perspektive von dem RP10-Projekt beleuchtet worden ist. Und da sind hier als 2 Beispiele einmal diese regulären, also die Beispiele, wo Holz einfach sehr, sehr strikt beim modularen Bauen eingesetzt wird, wo es einfach viele Wiederholungen gibt und dann wenige Fälle, wo sich die Sachen einfach ja, Ausnahmebauwerke, wo sich das Ganze eben doch individueller gestaltet, und genau da haben wir wahrscheinlich noch viel Potenzial für die Zukunft. Wir haben diskutiert am Ende, haben wir heute auch wieder vor. Und hier so ein kleiner Auszug aus den Topics. Also es ging ein bisschen ein Stück weit um die Flexibilität beim modularen Bauen, die natürlich erstmal nicht so ganz stark gegeben sind, wobei es dann auch immer die Frage sich gestellt hat, welche Flexibilität braucht man und welche wird nachher wirklich auch in der Praxis genutzt. Wir haben auch diskutiert die Herausforderungen beim sozialen Wohnungsbau, welche Auflagen damit eben einhergehen, und genau, einiges eben besprochen. Ja, und damit wäre ich eigentlich auch noch nicht ganz am Ende des Rückblicks. Also das waren letztlich die 3 Vorträge. Wir haben auch ein paar News. Wir sind mittlerweile online, jetzt schon seit ein paar Monaten, aber seit dem letzten Treffen, glaube ich, da waren wir noch nicht online. Das war im Januar. Das heißt, hier einfach mal die Info. Da sind auch immer Beiträge jetzt von uns oder aktuelle News kann man da finden. Und ansonsten hatten wir kürzlich bei uns einen Workshop, Tree to Product, mit einem Gastprofessor Martin Tamke von der CETA-Universität aus Dänemark. Und bei dem Workshop wurde mal beleuchtet, wie sozusagen dieser ganze Workflow aussieht, vom Wald bis zum Produkt. Also man hat wirklich angefangen, beim Wald zu schauen, wie ist der Bestand, bis hin zur Wertschöpfungskette, ja, die Sägewerke und auch nachher die Produkte. Als Beispiel von den Produkten hatten wir da dieses selbstverformende Holz. Und genau, das war auch mal wieder ein Präsenztermin hier bei uns an der Uni. Und genau, ganz kürzlich hatten wir Besuch aus Finnland. Das waren ja, so eine kleine Delegation, die über das MRR, das Ministerium, an uns herangetragen worden sind. Wir haben uns mit denen ausgetauscht, haben in dem Zuge dann auch in Waiblingen das LCRL besichtigt, also die ja, Roboter-Experimentierplattform vor Ort. Und genau, das war eigentlich so die letzte Live-Aktivität von uns. Ansonsten gibt es demnächst auch noch über Constructive Conversation. Das ist auch so ein regelmäßiger Termin jetzt über das IntCDC. Gibt es eine Veranstaltung, wo der Oliver David Krieg zu uns kommt. Der war früher relativ ja, einer der ersten hier beim ICD. Der ist jetzt in Kalifornien und wird uns entsprechend hier einen Gastvortrag halten, und das soll dann meines Wissens in einer hybriden Veranstaltung münden. Aber da gerne nochmal auf die IntCDC News-Seite schauen, da wird man entsprechend auf dem Laufenden gehalten. Ja, und damit soll es genug meiner Worte sein. Ich würde den Bildschirm einmal entteilen und dann kurz unsere erste Vortragende vorstellen. Und zwar, das ist Katrin Jonas von Gropius, der Gropius AG. Und Katrin Jonas, she's working. I switched to English now because she will make an English lesson, so a lecture. So she's working on Gropius as a system designer for the Gropius building system. And she initially she was trained as a silversmith and a goldsmith and studied material-based product design before she steps in the architecture. She was in the UK, then at the Architecture Associate School of Architecture, and Achim Menges, which is now the speaker of the IntCDC, was at that time her studio master. And yeah, there she learned about the theory and design methods such as form finding and artificial evolutions. And at that time also the idea from TESSA was born at yeah, that time. And today TESSA is a side product from this research, and it's on the one hand it's design engineering, geometric geometrically complex structures. And on the other hand, it's for the computational design tool. And yeah, after 15 years of studying and working in the UK, Katrin is back to Germany now. And we are happy to have her here and that she will hold the next lecture for us. And yeah, Katrin, you are welcome to share your screen. And I'm not sure if you are there. Yeah, okay, we can see your screen. Great.
Yeah, okay. I start from the beginning. So yeah, thank you for the introduction, Moritz. Maybe I should add that after studying at the Architectural Association, I worked at ROBOTIC and then went to Borough Happold, where I stayed quite a long time, and I did an applied research with them, like an engineering doctorate, which means that I was working on real project, and at the same time I was pursuing a research project. And yeah, throughout this whole time, this idea of TESSA since the AA was the foundation of that research project. And yeah, so I just wanted to add that because this work very much refers to the work I did at Borough Happold, which is the engineering, like the support of the design engineering of complex structures. And I guess we'll talk later how that relates to this forum. So I just start this. TESSA is made for architects, designers, and engineers. And it addresses that high quality complex form in architecture is a challenge. And the challenge is to keep the design control and to balance cost. That is because complex form is in the common realm is broken into building parts as the last step of the design development process. So that is that the overall form of a complex structure is usually perceived first and then is broken down into building parts. So most of the time the process of post-rationalizing it to control the cost. And yeah, this affects long design development cycles and the manufacture of many different parts. So TESSA is kind of offering an alternative approach to this. It doesn't say that the common realm is the wrong approach. It serves a certain purpose, but there is a different approach to it possible, which is to design the parts first and then to design with them. So TESSA, that makes TESSA a growth model, which means the growth model is the digital model of elements and rules how these elements come together. Like the first instance of a growth model that became known is the shape grammar by Astrid Lindenmayer, which is a model that allows to study the growth of plants. One of the challenges here is that most shape grammars provide a model that creates branching structures, and so the question: how do you get to a growth model that's suitable for structural form growth? But I did the same. Like I defined, like just to study it, like the relationship between global and local geometry. I took the same element and used a quadrilateral equilateral triangle with the same, like all sides are the same, and I defined a constraint, like I constrained the angle in which they connect. And what you get is the gaps or overlap, the branching that I mentioned. So it's really kind of frustrating. And I then conducted many experiments on trying to overcome this, and I came up with a lattice-based process that I call the unit cell approach, And I went to two different applied math departments because I said, this is so constrained, there must be a much more free way to design a kit of parts, really. And Professor Keith Ball just said bluntly, you cannot grow form in a naive way. And this kind of quote has stayed with me and served to be true since he said it to me, which is now quite a few years back. So TESSA is a buildable growth model and has become a patent-filed method to create families of parts that combine and recombine to form continuous articulated surfaces. And with continuous, I mean like gapless closed surfaces. And it considers that the discretization of form is a multidimensional task. So whoever has worked on complex design geometry will know that there's a relationship between the shape, the three-dimensional articulation, whether it's planar or whether it's articulated. And then the physical offset is a big issue. Sometimes a surface, a design surface works on the outer design surface. As soon as you start building up the layers of material, the geometry doesn't work anymore. And the connection to neighboring parts. So these things are all considered in that growth model. And here you see TESSA at the moment implemented in Rhino 3D, and the slim version exists as grasshopper component. And it has the mechanism to generate these kit of parts, these families of parts, the different base geometries. You can define the shape, then the size of the shape, and then the articulation of the shape, like the degree of curvature. And then it generates you a respective family, and depending on the shape, the basic family is large or smaller, depends on the combinatoric of edge types, and then you can make a sub-selection and create, like, combine and recombine them. On the right side, you see a random configuration, which is one application format that you could just randomly connect it to each other. And you see here, there are two representations considered. There's a surface, like a tile representation, and then there is a frame representation. It's like two different codes sitting behind it. And then how you apply it, as I mentioned before, is like you can just take these kit of parts and manually put them together. Then you can grow them randomly, as I showed on the right side in the images before. And the initial application, how it came that that TESSA was developed, was that it was part of a genetic algorithm, like a multi-objective optimization process, like a much grander idea, where I wanted to combine form generation with form optimization. And I needed a growth model that represented buildable parts, and that is where TESSA came from. In a later stage, so that was part of my research, and then at University College London, together with Bora Happold. And afterwards, I've been approached and said, oh, it's such a simple and useful application. Why don't you make it usable for practice? And there, the genetic algorithm wasn't the way forward. It was like the two, like it's, as it is currently implemented as a top-down approximation of an input surface, or a growth of the element family onto an input surface, like a bottom-up approach. And here you can see an example of the same surface is tessellated with different families. It's the same shape, it's the same size of the shape, but it's different sizes of families. So with a large number of family has different types, you come closer to the input surface, and on the left hand you have a great, like, stepping faceting of the surface, but you have very few types. Here you can see the same example, like but different, again, different features, like you have the same square, one's big, one's small, and you see how the interpretation of the reference surface is different. And at the bottom you have a mixed mixed tessellation, like a rotated star tessellation pattern, and a quite fine match of the input surface. Because I had access to it, I dared to use the original model of the Great Court Roof by Foster and Partner that was engineered by Buro Happold, and it's obviously a form-found geometry because it sits on an old structure, so I wasn't allowed to put any structural forces into the existing building, but had to be transferred through additional columns. And so it's a form-found, it's a perfected shape of the roof. I just played with the idea, how about making it cheaper, or making, giving it a different tessellation. So I played, I applied TESSA onto it, like a triangulation, a coarser triangulation, again, the rotated star pattern, and squares. As an example for this presentation, I choose like a simple application that I work on with Hologram. Hologram provide an interface for mixed reality for Rhino 3D. So they are fostering the idea to build without any construction documentation, so that you literally build into air, like you have a hologram of what you want to build, and then you build onto it. So here you can see for bricklaying how that works very nicely. And we said that we want to make a workshop together. So in TESSA, TESSA provides basically the kit of parts that can be assembled, and to make it quite tangible, like easily to understand, we said we would use the smallest family of parts, which are derived by triangles. Then we define surfaces. We approximate them or describe them with these three elements. And then I said, okay, what would be a fast and not so expensive, simple detailing of the parts? And I decided for like aluminium sheet that could be folded. And you can easily, like TESSA would provide a color coding, but here you have these little wings, and when the wing goes up and it's a bit shorter, then it connects to the other one that's short, and if it goes down, the edge of the wing is a bit wider, and it connects to all the other wings that go down. And to go back to the example surfaces, that is what it would look like. And here's the other one with the same elements. That's what that would look like. And if you were to change the detail of the elements, then that's the same surface, but a different detailing of these elements. So just to summarize what TESSA is an integrated design system that considers material manufacturing construction constraints, and all outcome is by default pre-rationalized. So coming back to the initial introduction, where I said that in the current realm, most complex form is post-rationalized. When you predefine the elements, then yeah, they are pre-rationalized. If you consider manufacturing or transportation, and material constraints, of course. So here are a few application examples. It's not that's not done with TESSA, but it's kind of the kind of project that application that TESSA could help is for roofs, envelopes, floor tiling, substructures and facades. And what was a very nice experience for me was that Patrick Schumacher was invited to the launch of TESSA from Tim Stoner. I don't know if Tim, you are in this call. He was invited to the launch, and I was very nervous because I thought, oh no, Zaha is only working on freeform and it's about smoothness, and TESSA has this kind of constrained geometry. It works with constrained geometry sets, so you mostly have facets. But then Patrick was one of the first who really noticed that it was not so much a post-rationalization tool, which you could use it for, but that is really an opportunity to define like signature designs or your personal kit of parts, so to say, and apply to different structures. And I show this this project by Foster and Partner that again Bro Hubbard had engineered, because it basically refers to a square grid, but it's a highly modular project, and I bring that in because it kind of revives the idea of modularity in architecture that for a long time has been not so popular. And kind of what TESSA is doing is basically going that next step that you can scale modularity in the shape, but also you can go into the third dimension. And that is something that is possible through computation. I mean, is facilitated through computation. And what I think, or what made me pursue this project, was that I really wanted to have working design frameworks where the concentration is then not any longer on the problem solving, but on actually building on a system or design framework that works, and kind of putting in the depths of the design and in the detailing. And this is why I show this project, because I think it's just very, very beautiful. So a lot of people have worked over the past years on this project, supported it greatly. The core team is just 3 people. Myself is Tim Stoner of Space Syntax and Igor Siveroni. Yes, and that's it from my side. Thank you.
Okay, yeah, thank you, Katrin. Looks very nice, I think, and interesting. What's possible with TESSA, and yeah, maybe we can open the questions to the audience. We are not too many people, so it should be easy to yeah, just make a question. Is there something? If not, I would have one first and maybe another, but yeah. So yeah, how does it actually come that that you come to Germany after that long period of time in the UK? So and you started at Gropius. Can you say how this happened?
Yeah, well, it's a bit independent, I have to say. So being in Germany and being in Gropius, but I think like maybe the connection to Gropius is, yeah, I guess we need to explain also what this project has to do with this forum, and how I got to Gropius, who are doing who set the mission to create sustainable living for everyone. So residential living and wood structured, multi-story wood structures. And they actually approached me because I had worked on, because of TESSA. So they were interested that I had developed an integrated system, like a scalable modular system that integrates physical criteria, and that is I mean, that was my question to Gropius as well. Like, how can I help? And it was, I guess, it's the idea of systemization in what they want to do. And the challenge there is the combination of automated planning, so automated site-specific building configuration, and the other hand, robotic manufacturing, and in the middle, performance optimized design. And so we're developing a building system that's meant to be, is like almost like growth model. So you have elements and you have rules how these elements come together, and these elements have to be integrated, as in that they need to consider all the systems that a building needs to have, like all the technical subsystems. And yeah, so that's how I got to Gropius. So I'm working on the building configuration side, like making the design of the growth model. Like there are modular building like layouts that are kind of aligned with the product definition. So we drive the whole, like Gropius drives the entire building product as a product. So we also have user research and find out what is wanted by the market, but also by the clients, like the future tenants. And all this has to go into this growth model, if you want.
Okay, thank you. And I think that also answered my second question I would have to, are there other possibilities to use this kind of concept? I mean, of course, in this case, the tool is like for the surfaces, but in a way, you told us that it's a similar approach, what you do at Gropius, that you yeah, put this together and treat it as a product. So yeah, the other question would be, is it possible to make this growth approach available for defining rooms and spaces? So yeah.
Yeah, I mean, it's an approach, right? It's something that is not that new yet to architecture, but I mean, this kind of bottom-up approach is something that, as I mentioned in that presentation at the beginning, it's just not so easy to define what the paths are and how they come in. So, but this bottom-up approach, like this growth approach, is definitely, that's, as I said, like in this automated planning of buildings, that how it's happening. It's not a parametric model. It's a growth model. So it's aggregating predefined modules to create adaptable buildings, site-specific adaptable buildings. So yes, this approach, I mean, to answer your question, yes, this approach and kind of the underlying idea of bottom-up growth of structures is definitely applicable to different projects and different use cases, if you want. I mean, this is a really big step, right? I mean, what I was doing on complex form and then being in kind of residential building structures, and that bridge has been made. I mean, I didn't make that connection. As I said, it was an engineer who approached me from Gropius. But yes, there are different applications, definitely.
Okay, yeah, thank you for the lecture and for the answers. And maybe we have some more answers. I hope Jakob arrived. I'm not sure. I wrote him. So we just discussed before that it's Friday the 13th today. So maybe this is glancing here also.
No, it brings luck. We said it brings luck.
Okay, but Jakob is still not there. Okay, I don't know.
I
Yeah,
think
maybe.
he might be on the way from Weiblingen to Stuttgart. Yeah, but
Yeah.
that's all I know.
Okay, so we need some more questions actually to yeah. So I'm done with my question. Maybe there's something from the audience. Would be nice. Just to Jakob is calling.
Maybe another question, as you showed,
great.
Katrin, you're working with flat elements, with flat surfaces. You multiply them to approach to a free-form surface. But the project you showed from Fosters and Partners was, let's say, with curved elements. So is it possible with the tool also to work with curved elements, with, let's say, free-form components, which are then used as a repetitive elements in the tool?
Yeah, that's a good question. Well, how the element, like, first of all, going back, TESSA is actually not working with planar elements. It's one thing that distincts it from other approaches. If you've seen the initial, depending of course, the triangles, they're always planar. But as soon as you have a basic square family, they have a curvature. And that is kind of because there's a lot of research done into planarity. And I said, if you can control the types of curvature you have in your kit of parts, then it's not a problem to have curvature, depending on your material, of course. But so they are like most of the families are by default curved, but you could, of course, then triangulate them and make them planar. But yes, the articulation inside is free. It's just a placeholder, as you saw with the triangles. Like the tessellation you get from TESSA is a placeholder. But then there's certain rules how to create the offset and to the neighboring parts, and to ensure that they can combine and recombine. So it's just the rules by detailing that design that allow you to make freeform of the elements inside can be wild if you want.
Okay, but as a, let's say, as a producer of such structures, we always need to hope that the designer already used the tool, so we have the repetitive elements, or maybe it's a tool for us to approach to a design was completely free and not repetitive.
Yeah, I mean that's why I said to Julia and Moritz that TESSA has been a little bit before its time. Because it's the question, where do you place it? Is it kind of a manufacturer's tool, or is it a designer's tool, or is it the engineering post-rationalization tool? And for me, it's definitely a designer's tool, but the design operation works, the operational, like the day-to-day work is different. So you actually have to introduce a different culture of working, like local parts, global parts, and give back that design control, which is what is in my interest, like to enable a designer and to work with a design framework that really ensures that what you create can be built, and you can create like design that bring design depth to it. So yeah, it's just about placing it. I mean, it's kind of an old approach, newly thought, right? Because if you know masonry, then there is also predefined discrete parts, and working with that and learning what you can do with that equally with wood. So it's kind of the same approach. It's just that it's material neutral. It's you as a designer then define, you know, if you take the triangulation because you want to have easy glass, like you want to work with glass and not curved glass, but then you say it can't be bigger than 2 meters or something because of cooling or transportation, then you have that control. So that's why I'm claiming it's integrated, an integrated design framework.
Thank you.
Thank you for